Hi everybody, welcome to, I can't remember what week this is now, although we're at the end of week 9 of the school term, so we're all getting to the pointy end. I think Ross just sent me his assignment draft, which I'm shocked about being on time. Everybody else I think is probably working on that now, but given that it's due this week. So we looked at amino acids and proteins and the structure of proteins. Does anyone know what an enzyme is, or what it does, or why the amino acids and protein structure is important when we're talking about it? Anyone? So Jacob says they speed up reactions in the body. Anyone else? So Ross says a biocatalyst, it's very specific. So they speed up reactions in the body by lowering the activation energy. So enzymes are proteins. They are biological catalysts, and the activity depends on the structure and the specificity. So catalysts and enzymes, a little bit of a recap. Only needed in small amounts. They aren't used up in the reaction, and they do not alter the position of the equilibrium. And they lower the activation energy required, or they lower the total amount of energy required for the reaction to start. If you think about, if you're in grade 12 now, you think about to grade 10. You look at the rate of reaction. So a reaction will only take place when there's enough energy in the system for that reaction to happen. Otherwise, the particles are just bouncing into each other and bouncing off, right? So the minimum amount of energy is required for them to stick together and the reaction to occur. So the idea is the biocatalyst or the enzyme lowers the amount of energy required for that to happen. So you can see that here in this graph. I'm going to use the whiteboard a bit today rather than just the slides, but it's quite a visual thing. So we have our uncatalyzed pathway here and our enzyme catalyzed pathway. So you can see here the amount of energy in the enzyme catalyzed. And so you can see there that the enzyme lowers that level of energy. So energy on the Y, reaction progress on the X. Doesn't actually change or alter the reaction in any way. but it speeds it up by lowering the energy required. Okay, so enzymes are proteins, inorganic catalysts. I do apologize. I feel like I've been punched in the face with a brick. Inorganic catalysts are usually metals, and they are unspecific. So magnetite, that's used in the production of ammonia, can be used across lots of different reactions, sorry. Whereas proteins, the enzymes, which are proteins, typically have one enzyme, one reaction that they impact. So I want everyone to take 1 minute and think back to last week and the 4 different structures of proteins and why they might be important here. So give everyone 1 minute to have a think. Oh man, I feel like death. Okay, so we have the primary structure, which is just the amino acids in sequence. We have the beta pleated sheets, which are the secondary structures. You have the tertiary structures, which are the 3D structures. And within these 3D structures, we have what's called the active site. And this is where the enzyme catalyzes the reaction. And this 3D shape that makes up the protein and makes up the active site is really important. If we change the primary structure, then we cannot, the protein will change shape and the active site will change. So, you remember tertiary structure, and it's influenced by the bonds between the R chains of the amino acids. So remember that, we've got our hydrogen bonds, we've got dispersion forces between the hydrocarbons, we've got the disulfide bridges, and we've got ionic interactions between positively and negatively charged R groups. So we've got the quaternary structure as well. So we talked about the specificity of the enzyme, and that is because of temperature and pH. So, because what happens if we change the temperature of the enzyme above a certain point, it actually changes the shape of the protein, which changes the shape of the active site. When we've got to go through those questions from proteins. We'll do that at the end. So temperature and pH. So pH is when we add H plus or OH minus to a solution that holds our enzymes. What it does is it adds H plus or it takes away H plus. And the enzymes bind really specifically based on the intermolecular forces that are present. You add H or take away H, and the enzyme will not bind to the substrate with as much specificity. So where we have the active site, the substrate enters the active site of the enzyme, and that is where the magic happens. So a lot of the time, this active site will form, hydrogen bonds, whatever kind of bonds with the substrate. And what happens by doing that, it actually destabilizes the rest of the molecule. And most of the time, it splits it in two, or it'll split it into two other molecules in intermediate stage. Now, we remember this is all determined by the side chains of the amino acids. So there used to be a lock and key model that we had an enzyme with a specific active site and a substrate with a very specific shape. So when the enzyme and the substrate link together through these intermolecular forces, the bonds in the substrate become unstable and they break, and we get a new product. Okay. So this would explain why the overall 3D shape of the protein is so important, because the substrate has to perfectly match. So everybody, again, I want everyone to take 60 seconds and think. Remember what an isomer is. So what is an isomer? Why might it be important? Okay, so Jacob says the isomers are the same molecules with the same molecular formula, a different arrangement of atoms in space. So think about, I can't superimpose my hands. They are the same. And this is what we call an enantiomer. So I want everybody to draw this if you're sitting and watching. You've got 60 seconds to draw this molecule. So if the lock and key model is true of enzymes, why would this be a problem? So Jacob said, if the substrate is an enantiomer and it binds very specifically to the active site, the active site recognizes this, but it won't recognize that. So now we have a problem. The lock and key model is great, but it doesn't always work. So, and it's not just that 2D looking molecule, the whole shape of the molecule changes. So right hand and right hand shakes well. Try and shake a left and a right hand. It won't work anywhere near as well. So phenylalanine on the left is what we use in artificial sweeteners. On the right is completely tasteless. I don't want you to draw that, but you will need to know that that was in an exam. But just have a look at it and see what's different. So here we've got the enzyme. You've got two binding sites where we have carbon double bound to oxygen here, interacts with an amine group in the active site. Here we've got another amine group, amide group even. And over here we've got oxygen. If I flip that molecule, even just like left and right hand, is it going to bind to those two spaces? If there was a different isomer, not fit as well into the active site, and the enzyme would not be catalyzed as well by the enzyme. And this is why the lock and key model has been refined since it was implemented. So the structure of the enzyme does actually have some level of flexibility. So the active site can change when we have isomerization. This is an evolutionary thing. If the enzyme only catalyzed that very specific isomer, we wouldn't really survive. So in an induced fit model, you can see it's not quite the right size, but the active site will change slightly to accommodate the substrate. It will not work perfectly with an isomer, with an enantiomer. So it would be, so for one of those molecules, it would work the best, and then it would still work slightly as an isomer. All right. I'm going to go through these questions now. Well, I'm going to go through the first 5, and then your exam questions will be the last 3, and then we'll go back through those protein questions. So, does a biocatalyst and an inorganic catalyst both lower the activation energy of a reaction? Is that a inorganic, enzyme, or both catalysts? So I'm going to give everyone 60 seconds. So both an inorganic enzyme, both an inorganic catalyst and an enzyme. So is an inorganic catalyst and an enzyme both highly specific, or just one or the other? Actually, I'm going to let you guys do these. I'm going to send these out with the slides. I'm going to go through the protein questions right now. Ones we did last week. You guys can do those, and we'll go through them in the next week as well. Just let me bring up the questions. All right, let's go through these questions that I said everybody has homework last week. So the image shows a section of the primary structure of part of a polypeptide. It consists of something amino acid units. 1, 2, 3, 4, 5, 6, 7, 8, 9 amino acid units that are linked together by amide groups. They're produced by a condensation reaction. So it's 2/3 leucine. It would be, I mean, it's not. 2 units of leucine even. 2 units of alanine. 1 unit each of valine, glycine, and lysine. Okay, so what is the secondary structure represented in the diagram? Any ideas thinking back to last week? So this is an alpha helices. You can tell by the ribbon-like shape. So if we remember back to our structure of amino acids, we'll know that there's an NH group and a CO group. The NH group being on the end of the amino acid, being the amine group, and we've got carbon and oxygen double bond as well. So we get hydrogen bonding between oxygen and hydrogen. Okay. So we have 5 different bonding interactions. So we have our 3 intermolecular forces. We have hydrogen bonding, dispersion forces, and we have, these are exam type questions that you're likely to encounter. So we've got hydrogen bonding, dispersion forces, dipole-dipole forces. We then have ionic interactions between positive and negative. Then we've got disulfide bonding, which is actually covalent bonding. Between the 2 sulfur molecules. So let's look at the comprehension part. So explain why it is important to be able to determine the specific sequence of amino acids in a protein. So we just looked at specificity of enzymes. Human insulin as well and bovine insulin differ by 3 amino acids. The human body knows that it's not human insulin because of the 3D structure of the slightly altered protein. So we can't actually use it. And to sort of put that into a nice, pretty sentence, because the primary sequence determines the secondary structures, which determines the tertiary sequence, which determines possibly the quaternary sequence as well. Okay, so alpha helices and beta pleated sheets. Well, the biggest difference, they're both formed by hydrogen bonds between the negatively charged oxygen and the positively charged hydrogen. But the alpha helices coil the protein, whereas the beta pleated sheets and the beta, well, actually, I realized I just skipped past question 5. So in order for the alpha helices to be created, the R groups have to be quite long because there's quite a distance in that coil between the oxygen and hydrogen. Apologies. Okay. So, question 7. This is where we need to think back to solubility. Everything that we learned in the first 4 weeks relates to this. So when the protein folds over itself, like this, it will fold itself into the least energy intensive way possible. What it does usually is it displays the R groups on the outside that are water soluble, and it tucks away the water insoluble. So anywhere where you've got a hydrocarbon will typically be tucked inside the protein. So if we think, I shouldn't have a list here with me, but some of the amino acids have carboxylic acid on the outside, on their R group, sorry. Others have just hydrogen. Others have just a CH3 group, or a methyl group, or an ethyl group, or a propyl group, one of them has. So they don't dissolve in water. So globular proteins, the whole idea is that they make literally a ball. And on the outside of that, little floppy R groups. Let's go here. A polar R group will be showing on the outside so that it dissolves in water. On the inside, you've got your non-polar on the inside of that globular protein. So that's why some proteins are water soluble, others are not. Sometimes you don't want proteins to be water soluble. Sometimes you want them to have to be carried around the blood by hemoglobin. So we know that if we heat up the protein, we will change the 3D shape of the protein. But if we alter the pH of the protein, then we get what you call ionization of the side chains coming off the amino acids. What that means is, because when we add loads of H plus or loads of OH minus, that's going to interact with the side chains. You add lots of H plus, all of those side chains become positively charged. Now we know that we need ionic interactions and hydrogen bonding for that to happen. So below a certain pH, then you've got too much positive charge. Above a certain pH, not enough positive charge. And remember that specificity of the enzymes. I'm trying to put it all together to enzymes because that's the idea of this. By changing the charges on the molecules on enzymes in that active site, it can't bind in the same way because we know that it requires that difference in polarity in order to bond. So that's why if we change the pH of the solution, the enzyme will not work because it will not have that specificity of binding. All right, I'm going to send you guys with the recording those questions. I would talk longer now, but I don't have any voice left. I think I'll do a session next weekend and then 2 in the holidays. There should be I'll do a bonus week because of that missed one I did in the middle, so it'll be 11 weeks. I will see you guys next Sunday, where hopefully I can speak a bit better.